Well, you're going to take a test, and then we're going to review factoring and the quadratic formula, and then you're going to review for the final. Because you have to do lots of factoring next year. So today we're going to go over symmetry. So this is going to start off a little bit easier. Please make sure you're paying attention towards the end of the lesson today, though, because I think it's something that you've never seen with symmetry before. So we're going to go over line symmetry, rotational symmetry, plane symmetry, and axis symmetry. Okay, so we are also going over symmetry in three-dimensional figures. Okay, so not just two-dimensional flat figures. All right, so in the animal kingdom, that's supposed to be an M, the symmetry of an animal's body is often an indication of the animal's complexity. Animals displaying line symmetry, such as insects, are usually more complex life forms than those displaying rotational symmetry, like a jellyfish. Okay, so over at the right here, we have line symmetry through this beetle, and we have rotational symmetry here through that jellyfish. So a figure in the plane has line symmetry if the figure can be mapped onto itself by reflection in a line called the line of symmetry. Okay, so we're taking part or half of an object or figure and reflecting it over that line of symmetry to create the same thing. So in this next section, we want to state whether the object appears to have line symmetry. Okay. If yes, draw the lines of symmetry and state the number. Okay, so letter A, your line is already drawn in here. This would be your line of symmetry. Okay, so it does have a line of symmetry, yes. This is the only line of symmetry that can be drawn in this figure. So I would say this has one line of symmetry. Okay, so we have to state how many lines of symmetry there would be and draw those in. Letter B. Again, these ones are drawn in for you. I have one line here, 2, 3, 4, and 5. Okay, so you would have 5 lines of symmetry for letter B. Okay, what about letter C? If I look at this picture here, do I have any lines of symmetry? No. Okay, so I can't draw in a line and have that same piece reflected over the line to create it again. Okay, so I don't see that reflection over that line of symmetry. Any line that you would draw in. Okay, does that make sense? A, B, and C? All right, I want you guys to do D, E, and F then. So draw in those lines. Okay, they're not drawn in for you. You have to draw in the line of symmetry, where you think that would be, and then tell me how many there are. All right, so letter D. This one, can I draw in any lines of symmetry here? No, you cannot.
Oh, that's good for her. If you take one side of it, it will flip and make some weird shape. You turn it the other way. There's no.
No. If like this way?
Yeah.
Because then this would be like here and then down here. It'd make a trapezoid.
Oh. You actually have to fold it.
Yep. So you have to pretend like you're folding it over. So even that diagonal line, if you were to fold it over, your corners wouldn't match up. They'd be crossed. Okay, so if I were to draw in the line here and fold it over, your diagonal corner would come up here. Right?
What if you do it like down the, like from the top left corner to the bottom right corner?
It's not possible.
Mm-mm. So, I mean, you can always take a piece of paper, make a parallelogram, and fold it different ways. It's never going to line up on itself unless it is a rhombus. Okay? Because a rhombus, all of your sides are congruent to each other. These ones, these two sides are not congruent to each other. Okay? Letter E, how many lines of symmetry do you have? You have one. Okay, and then letter F has 2 lines of symmetry. Okay, one vertical, one horizontal. Again, I can't do the diagonal ones because those sides aren't congruent to each other. Okay, lines of symmetry coming back to you. Yeah? I know you've done this before. All right, so a figure has rotational symmetry. So now we're moving on to rotational symmetry, not just line symmetry. If the figure can be mapped onto itself by rotation between 0 degrees and 360 degrees. Okay, so this rotation has to be between 0 and 360. About the center of the figure, called the center of symmetry. Okay, so you need to find the center of that figure. You need to take a piece of that figure and we can rotate it so many degrees to map out onto itself as you rotate it around. Okay, so with a square here, you would start at 90 degrees. Okay, so this figure has rotational symmetry, it's a square, of 90 degrees, 180 degrees, and 270 degrees. If I take each of those and rotate it around that many degrees, it will map out onto itself. So here 90 degrees, I would take this section and I'd keep rotating it 90 degrees all the way around and it would rotate onto itself. Okay, same thing with 180 degrees. You would take half of that, you can rotate it again 180 degrees and it would map out that second section there. 270 is taking this entire section here, and again we can rotate it all the way around and it'll still map out as that square shape there. Okay, so it's taking that section, rotating it, it still ends on itself. So we can do some examples of that on the back. Okay, so each of these we're going to state whether the figure has rotational symmetry. If yes, we want to locate the center of symmetry and state the order and magnitude of symmetry. Now when I say that, that means you have to state what degrees it can rotate through. So our square on the front, we could rotate through 90 degrees, 180 degrees, and 270 degrees. Now your degrees have to be between 0 and 360. Okay, for this first one, this one does have rotational symmetry. Okay, its center of rotation is the center of the figure. Now what I can do is split this into a piece of that figure, right? And I want to see how many degrees I can rotate it through. Well, to find how many degrees I can rotate it through, since a circle or a rotation is 360 degrees, right? I can divide by how many slices I can cut this into. So how many sections can you cut it into? Okay, so you can cut this into 6 different sections. So our starting degree that we would rotate this through is 60. Now, just like with your square, that's not the only degrees you can rotate it through, right? With our square, we could also do 180 and 270. Now, notice when I started with 90, if I add 90 onto it, I got 180. If I add 90 onto that, I get 270. So with this one, to find out our other degrees that it'll rotate through, we have to add 60 onto 60. So it can also rotate through 120 degrees. Add 60 onto that. And 180 degrees, right? I could split it right down the middle. Okay, rotate through 180. Add 60 onto that. Add 60 onto that one. Now, if I were to add 60 again, I would get 360 degrees. We don't want to write 360 degrees because then it just rotates onto itself. Okay, you take the original, you rotate it around itself, it stays itself. That's true for any figure. Okay, so we don't write 0, we don't write 360, but we write everything in between. Questions? Okay, so again, this one does have rotational symmetry. And it would be with 60 degrees, 120 degrees, 180 degrees, 240 degrees, and 300 degrees. All right, then looking at letter B. Letter B, could I split this into different sections and rotate them around a center to map out onto the same picture? No. Okay. You do have a center point of your triangle, but you can't split it into equal sections. Okay, since I can't split it into equal sections, this one does not have rotational symmetry. Okay, then letter C. Does this one have rotational symmetry? Yes, it does. Okay, if I put my center point right here, I can split this in half, and I could rotate this halfway around here. So I can split this into 2 sections and rotate it 180 degrees. Okay, so it would only have rotational symmetry. Of 180 degrees. Okay, so if you can split something in half and you can see that rotation of 180 degrees, it still has rotational symmetry. It's just 180 degrees though. Okay? Questions on A, B, or C? All right, I want you to do D and E then. Letters D and E. Do those have rotational symmetry? And then tell me the degrees that they could rotate through if they do. Can you split this into sections? So then we can
Next time you start to spot.
She'll appreciate that.
Probably.
So,
Yeah.
so where's your center? Yeah. Okay, so you said you can split into 5 different sections, right? So here we took 360 divided by 100. Yeah. So all of them are gonna do this. It can be we take 360 and divide by how many sections? Yeah.
Smiley face sticker.
And then complain that you can't log in.
I don't either. This is a lot of work for no result. Someone tell me anything.
It tells you how it rotates itself.
Why is that important?
It's symmetry. There's symmetry everywhere.
Exactly, what is he saying?
So I should only have 4.
Okay, I'm not doing this no shape. I know how to cut shapes in half.
Good job, Carter.
Symmetry's gone, right?
Yep. All right, letter D. Does this one have rotational symmetry?
No.
Yes, this has rotational symmetry. It does have rotational symmetry of 72 degrees, 144 degrees, 216 degrees, and 288 degrees. Okay, so you had 5 different sections, so take 360, divide by 5. Letter E. Does that one have rotational symmetry? Yes? How many sections does it have?
Oh, sections. Okay.
It has 3 sections here. Okay, so I would take 360 divided by 3, not 6. Okay, you have smaller petals and larger petals here. Okay, so this would be rotational symmetry of 120 degrees and 240 degrees. Okay. Off to the right there, I have point symmetry. Okay, so a figure has point symmetry if the figure can be mapped onto itself by a rotation of 180 degrees. So a playing card exhibits point symmetry. It looks the same right side up and upside down. Okay, so here's your point of symmetry. Okay, if I cut this in half, it would rotate around 180 degrees. Okay, our example of that from up here would be letter C. Okay, that has point symmetry. Okay, it rotates 180 degrees. Okay, any questions on our two-dimensional symmetries? Okay, then we're going to look at three-dimensional symmetries. Okay, so we have plane symmetry and axis symmetry. Now these are very similar to line symmetry and rotational symmetry, just in three-dimensional figures instead. So plane symmetry, we have a three-dimensional figure that can be mapped onto itself by a reflection in a plane. Okay, so you need to create this plane, right, which is a flat two-dimensional surface through your three-dimensional object. If you can create a plane and reflect half of your figure over that plane to create the rest of your figure, your three-dimensional object has plane symmetry. Okay? Now, axis symmetry, that's when a three-dimensional figure can be mapped onto itself by a rotation between 0 and 360 degrees. Okay, so you're still taking a chunk of that three-dimensional figure and rotating it around to get the rest of it. Okay, so it's very similar to rotational symmetry. We're just taking a three-dimensional object and rotating it instead. So in the examples below, we have our three-dimensional objects here. And we want to state whether the figure has plane symmetry, axis symmetry, both or neither. Okay, so in our first figure, letter A, can I take a plane and cut that figure any way? Okay, take a plane, can I cut it through the figure, take half of it, and map it onto itself? Yes, I can. Okay, that would be, try to draw the best I can here. If I take a vertical plane and sliced it right down the middle of that L shape. Okay, so I sliced it right down the middle vertically there. I could take the front half, reflect it over that plane to get the back half of that shape. Okay, so we do have plane symmetry. Okay, now I'm looking to see if I have axis symmetry. So can I take a certain section of this shape and rotate it between 0 and 360 degrees to map it out onto itself? Can I rotate any part of that? No. Okay, so this one does not have axis symmetry. Okay, so it does have plane symmetry, but not axis symmetry. All right, letter B. Does this one have plane symmetry? Can I slice through this and reflect it over a plane to get the same image after that reflection? Yes, I can. Okay, so if I slice it again vertically down the center here. Okay, right down the center vertically. Okay, I can take that right-hand side, reflect it over that plane to get the left. Now you could also slice it horizontally through the center here. Okay, so if I slice it horizontally through the center, I can take that bottom half, reflect it over that plane to get the top half. Okay, so this one has two plane symmetries. Okay, so that one has two plane symmetries. What about axis symmetry? Again, this is where we're taking a chunk of our figure and we're rotating it around a center point. If my center point is here, I can split this into 5 sections. Okay, so I can take that section and I can rotate it around 5 times. Okay, so this one does have axis symmetry. Okay, and just like with rotational symmetry, I do want you to write out the degrees that it can rotate through. Okay, so I could take this chunk right here, rotate it all the way around. Since there's 5 different ones, we take 360, divide by 5. Okay, and we do get 72 degrees. Add 72 to 72. 144 degrees. Add 72 to that. That's 216 degrees. And 288 degrees. Okay, so with our three-dimensional objects, it's very similar to our two-dimensional objects. Okay, plane symmetry is similar to line symmetry. Axis symmetry is similar to rotational symmetry. Okay, they're just in different types of shapes. Questions on letter B? All right, letter C. Does this one have plane symmetry? Can I take a plane, cut through it, and reflect it over to get the same side? No. What about axis? Can I take a section and rotate it all the way around to get that same figure?
No.
Okay, so this one has neither. Okay, so no plane symmetry, no axis symmetry. All right. Letter D. Does this one have plane symmetry? Can I cut through it any way, reflect it over itself? Yes, I can. Okay, so I could cut it straight through the center here. And reflect it over that plane, and it'll map out onto itself. What about axis symmetry?
Yes.
Yes, it does. So if you take the very top of this baseball bat, right? And you can rotate it all the way around itself from the very top. Now, since the top is circular, right? It's not cut into specific sections. Okay? You would say this has axis symmetry. Okay, for angles between 0 and 360 degrees. Because you could rotate it through 0.5 degrees and it'll map out onto itself. You could rotate it through 17 degrees. It'll map out onto itself. Okay, you could rotate it through 25.425 degrees and it'll map out onto itself. Okay, so you want to say if you have that circular figure, it has axis symmetry for angles between 0 and 360. Does that make sense? Okay, if it has that circular part. So there's one on your assignment.